What is the average income of American households? Each March, the government's current population survey asks detailed questions about income. The random sample of about 60,000 households contacted in March 2012 had a mean or a total money income of 69,677 in 2011. The median income was lower, of course, at 50,054. That 69,000 describes the sample, but we can use it to estimate the mean. So parameters and statistics. As we begin to use sample data to draw conclusions about a wider population, we must be clear about whether a number describes a sample or a population. For the sample of households contacted by the CPS, the mean income was X bar equals 69,677. That number is a statistic. Because it describes this one CPS sample. The population that the poll wants to draw conclusions about is all 121 million of US households. In this case, the parameter of interest is the mean income of all these households. We don't know the value of this parameter. So this is just trying to give you a definition of the difference between a parameter and a statistic, and we'll keep going with that and you'll know what it is. So your homework and what you're working on today is basically defining what a parameter and a statistic is and what your population and what your sample is. So the value of a parameter is usually not known because we cannot examine the entire population. The value of a statistic can be computed directly from the sample data. We often use statistics to estimate an unknown parameter. Right. So remember S and P. Your S, statistics, come from samples. And parameters come from populations. And remember, we may not have exact parameters because it's through the population, but the statistics should be exact. As long as we're doing data analysis, the distinction between population and sample rarely came up. So we haven't really specified if it's from the population or if it's a sample from the population. Now, however, it is essential. So the notation we should reflect this distinction. For instance, we write mu for the population. So that's the population mean. And remember, I told you that later on we would talk about which one we use, mu or x bar or whatever, but it didn't matter at that point. Now is when it matters. And x bar for the sample mean. So mu equals population mean, x bar equals sample mean. You need to make sure that you know that. Otherwise, you're going to get it wrong on the AP exam, okay? Don't mess it up. Okay. When we flip it, we use just P to represent a population. Proportion the sample proportion is P hat, is used to estimate the unknown parameter P. Okay. So this example is what you're going to be doing for your homework tonight. You're going to identify the population, the parameter, the sample, and the statistic in each of the following settings. And you're going to check your understanding that comes next. You're going to do the same thing. So these two are where we're supposed to stop today. But like I said, I'm going to keep going a little bit so that tomorrow is not as long-winded. But you won't have homework on anything past these two examples. Okay. So this is all you're going to have homework on. So we're going to identify the population, parameter, sample, and statistic in each of the following settings. The Gallup poll asked a random sample of 515 U.S. adults whether or not they believe in ghosts. Of the respondents, 160 said yes. So let me do this one for you, and then you guys can help me out with B, okay? So we're going to talk about our population first. Your population is your overall. Where are we pulling the sample from? So it says the Gallup poll asked a random sample of 515 U.S. adults. So what did they ask? They asked all U.S. adults, or that 515 came from all U.S. adults. Sometimes it's easy to do the sample. I'm leaving a space so we can do the parameter after that. So if the population was all of them, the sample was the 515 U.S. adults interviewed. I don't care what order that you put them in. Like I said, sometimes it's easier just to go from your population to your sample, because if you know what your population is, you know what your sample is. Your sample is always from your population.
Are they ever going to tell you like what the specific population would be?
They
Like,
do.
Is it always going to be like all?
Mm-hmm.
Okay,
Yes. So like this, we had a sample of U.S. adults. So where did the sample come from? All U.S. adults. It could be all high schoolers at a large high school.
Yeah.
You know what I'm saying? Not all U.S. high schoolers, but all high schoolers at a large high school. Okay. It just depends on what they give you in the context. All right. So our parameter is what we're looking for. So it said of U.S. adults whether or not they believe in ghosts. Of the respondents, 160 said yes. So what were we looking for? We were looking for, that should say proportion, sorry. The proportion of U.S. residents. That believe in ghosts. And your statistic is the actual number that they give you. So they said 160, but remember that's out of 515 because we're looking for a proportion. Or 0.31. That say yes. To believing in ghosts. So again, your parameter is your overall proportion, just what are they asking you to find? And your statistic is what you actually found, okay? So again, population is where did the sample come from? The sample is what is the part of the population. Parameter is what are they asking you to find? And the statistic is what did they find, okay? So if we look at B, I'm trying to make it so you can see everything. We start with our population. It says during the winter months, the temperature outside the Starnes' cabin in Colorado can stay well below freezing. We've heard this scenario before for weeks at a time. To prevent the pipes from freezing, Ms. Starnes sets the thermostat at 50 degrees Fahrenheit. She wants to know how long the temperature actually gets in the cabin. A digital thermometer records the indoor temperature at 20 randomly chosen times during a given day. The minimum reading is 38 degrees Fahrenheit. So what is the population?
All indoor temperatures on a given day.
And not just indoor temperatures, but indoor, oh, I would say recordings or readings. Okay, so make sure you make it a little bit more specific, but that's perfect. I'm gonna write parameter, but I'm gonna skip, like I said, I like to skip to the sample. What was our sample of that population?
The 20 readings,
And be specific, the 20 what?
randomly chosen times during a given day.
You could have said the 20 randomly chosen readings during the day, that's fine. What are we actually looking for? The actual parameter, what are we looking for? What did she want to know?
how close the cabin is.
We wanted the true min temp. You could have said how low the temperature actually gets in the cabin. That's perfectly fine. Mackenzie, what you said is perfectly fine. Your statistic is what was the actual minimum. Well, there you go. So the minimum temp was 38 degrees. All right, we're gonna flip it over and you're gonna do it again. All right, so there are a couple different ways that they can ask you about this, and this is the first one where it just tells you to list it out. The second one, it says each boldface number in questions 1 and 2, I guess should say are, but is the values of either a parameter or a statistic. In each case, state which it is and use appropriate notation to describe the number. Okay, so remember, parameter is mu, sorry, and your statistic is X bar. What does the parameter deal with?
Population.
Population. I'm gonna put that in parentheses to the side that you can remember. And then the sample is the statistic. Sometimes that's the easier one to pick out first. It doesn't matter which one you do first, I don't care. Okay. So number 1, we're gonna find the parameter, and remember that's mu. And then we're gonna find the statistic, that's X bar. On Tuesday, the bottles of Arizona iced tea filled in a plant were supposed to contain an average of 20 ounces of iced tea. Quality control inspectors sampled 50 bottles at random from the day's production. These bottles contained an average of 19.6 ounces of iced tea. So which one was the population and which one was the sample?
The population would be.
Okay, we're just looking at the bold numbers, so check out the bold numbers. So we're either looking at 20 or 19.6. One of them is from the population and one is from the sample. 20 is the population. And that makes 19.6 from the sample. And again, here's how you know. Quality control inspectors sampled, it should say sampled, sorry, 50 bottles, and those bottles had an average of 19.6. So this is the average for the sample. This is what every average should be. The entire population should be close to 20. Got it? All right, we'll get number 2. All right. Parameter and statistic. Read it really fast. It says on a New York to Denver flight, 8% of the 125 passengers. Now, what are we looking at this time? Let's just talk about the boldface number. What are we looking at this time? The percent. So that's going to be a proportion. So actually, both of these are going to be p hat. Both of these are going to be p hat. So what is the difference in the notation? P hat deals with a percentage or a proportion. Okay, so make sure that you know that. Okay. 8% of the 125 passengers were selected for random security screening before boarding. According to the Transportation Security Administration, 10% of passengers at this airport are chosen for random screening. So which one are the population?
2%.
The 10%, that's everybody at the airport. And then the 8% are of a sample of 125. So from the sample of 125, or the statistic is 8%. Okay. Any questions? So again, at this point, and if you guys want to draw a line, you can. This is all your homework's going to be on, but I'm going to go ahead and teach a little bit longer so that we'll have a little bit less teaching tomorrow, okay? What we want to do is finish up all of 7-1 tomorrow, and I don't want to do like 6 or 8 pages. I want to go ahead and do some more. So we're going to go ahead and move on, but your homework will not be on this, okay? That's where your homework stops. So sampling variability. How can X bar, based on a sample of only a few thousand of the 121 million American households, be an accurate estimate of mu? So how can the sample mean be an accurate estimate of the population mean? After all, the second random sample taken at the same time would choose different households and likely produce a different value of X bar. This basic fact is called sampling variability. The value of a statistic varies in repeated random sampling. To make sense of the sampling variability, we ask what would happen if we took many samples, and here's how to answer that question. You're going to take a large number of samples from the same population. You're going to calculate the statistic, like the sample mean X bar or the sample proportion p hat. for each sample. You're going to make a graph of the values of the statistic. And then you're going to examine the distribution displayed in the graph for shape, center, and spread. As well as outliers or other unusual features. So this next activity we're actually going to do as a class, but we're not going to do it today. We're going to do it over the next 3 days. So I'm going to have you guys do it when we get some time. And then I think there are 10 or 11 that come on B day, and I'll have them do it as well. So then on Friday, we'll go over this activity and I'll get it to relate back to what we're doing, okay? So that's what the chips are for, all right? If you're remote, you're not gonna be able to do the activity, just follow along with it, all right? So what we're gonna do is I already have some chips, prepared a population of 200 colored chips with 100 of them being red. The parameter is the actual proportion P of red chips in the population. And that means that it's going to be 0.5 because it's 50%. So there's 200 chips, 100 of them are red, okay? In this activity, the class of 35 investigated sampling variability by taking repeated random samples of size 20 from the population. He has each student shake the bag, reach in and pull out 20 chips, noting the sample proportion or P hat of red chips. When finished, the student would return all of the chips to the bag, pass the bag, and the next student would repeat the process. Each student then recorded the P hat value in a chart and plotted this value on the dot plot. And it says here's the dot plot, but we're not doing it yet, okay? We will describe what we see. This will be our actual class data. And again, I'll go over this on Friday, so we'll come back to this. So we're gonna talk about shape, center, spread, and outliers. So if you forgot what those are, just make sure you review those. We will review on that day as well as next couple days. All right, so of course the class only took 35 different simple random samples of 20 chips. There are many possible SRSs of 20 from the population of size 200. If we took every one of those possible samples, calculated the value of P hat for each, and graphed all of those P hat values, then we'd have a sampling distribution. Now we're going to see another example of this, but I thought I'd make it a little more hands-on this time. We have time for it, and I actually got the chips, so we'll be there. All right. We'll do just a couple more pages, and then we'll be done. Okay. It's usually too difficult to take all possible samples of size n to obtain the sampling distribution of a statistic. Instead, we can use simulation. You guys remember that coin flip thing that we did earlier in the year, that simulation that we did? To imitate the process of taking many samples and create an approximate sampling distribution. So reaching for chips, we did this on a simulation. It's the same exact thing that just happened. The only difference is we used Fathom software to simulate choosing 500 SRSs. So pulling out 20 chips 500 times. So pulling it out one time, recording, putting them back in, pulling out a second time, doing that 500 times of size 20 from a population of 200 chips. We are obviously not going to do it 500 times, but the more that you do it, the more accurate it becomes, okay? So 100 red and 100 blue. The figure below is a dot plot of the values of P hat, the sample proportion of red chips from these 500 samples. So you can kind of see, those of you at home, if you don't have the printed out notes, you guys can kind of see, if I make it a little closer, that these are all kinds that you can see all these little dots on there, whatever. They're really overlapped on each other, so all of these are the 500 samples. So there's 500 little singular dots on here, okay? So A says there is one dot on the graph at 0.15. Explain what this value represents. So this dot right here, what does it represent?
Possible outlier.
But what it wants to know, yes, you are not incorrect. But what is the actual like meaning of that dot? What does this stand for, this p hat?
Percentage,
A percentage, right? So where is this at?
15%.
So 15%. Or that would be 3 out of 20 red chips for one SRS. Remember, that's one singular dot, one SRS of n equals 20. So this is part A. All right, so part B says describe the distribution. What do we need to do to describe the distribution? I'm going to do it up here so you guys can see it. What are the things?
Spread,
Okay, before that,
shape,
shape, center, spread, and last one. Come on, guys, Zoom, you can help too. Outliers. So what is the shape for this one? Zoomers, answer.
Unimodal.
Unimodal. Keep going. One more thing.
Symmetric.
Good. You can say approximately symmetric too, just to cover your tail if you want to. This looks pretty symmetric. It's a little bit off, but it's not too bad. All right. Center. Where's our center at?
0.5.
Where you could say that it peaks at 0.5.
Just say 0.5 will work on the
Uh-huh.
decimal.
Mm-hmm. You could even say approximately 0.5 because if you say it's approximately symmetric, you know what I'm saying, that may not be your max. Okay. So what about your spread? So typically if we try to say 0.5, the reason we put peaks at 0.5, either one is correct. Is just so you know you didn't label that a mean or a median. So that way they don't say, oh, well, you said it was a mean. Now you have to use IQR or whatever. Like you don't have to, sorry, standard deviation. You don't have to do that. So you can pick what you want. So on this spread, I'm not picking out anything other than the actual spread. So what is our spread?
0.15, 0.8.
Good. But if you define the center, you need to make sure that whatever you choose for the spread goes with that specific center.
Will it come off if you don't define it?
Depends on what it is. If it gives it to you, like in the, you know, the little boxes that we get that have all the data and it tells you specifically this is the center and this is the median, yes, it will count off. Okay. But on this, you can't tell what is what because you don't know all the facts. Okay. What are your outliers? Are we going to say specifically 0.5, 0.15, I mean? Yeah, or we can just say a possible at 0.15. What would we do to figure out if it was a for real outlier? You know everything. You know everything. Yeah, the 1.5 times IQR formula, or if you put it in your, like if you had all the data and you could put all 500 in, you could make your box plot with the little dots on it, and then you could see if there are outliers. But on this one, we don't know if this is a for real outlier, but it lies further away than the rest of them. So we're going to say that it's a possible outlier. All right. Any questions on A and B? Those are basically just review questions. Look at C. Would it be surprising to get a sample proportion of 0.85 or higher in an SRS of size 20 when P equals 0.5? Justify your answer. Okay. 0.85. Do we have one of those? How many times did we do this? We're going to do it just like 25, but this one is 500, right? We did this 500 times. In 500 times, did we get a 0.85 or higher? All right. So would it be surprising to get the sample portion of 0.85 or higher? And then why?
Because it happened 500 times.
Okay. So it's unlikely because 0.85 never occurred. In 500 SRSs. Now the question is, could it occur? Could it?
Yeah.
Yeah, absolutely. You could get all 20 red. What is the likelihood of that happening? Slim to none. Okay, because in 500 that never even happened. So that's why it says it's unlikely. It doesn't say it is not possible. Okay, so watch the way that it words it. And then D, part D. Suppose your teacher prepares a bag with 200 chips and claims that half of them are red. Claims that half are red. A classmate takes an SRS of 20 chips. 17 of them are red. What would you conclude about your teacher's claim?
It was like more normal.
Was it? So if 17 are red, what percentage did they get? Y'all have calculators? Anybody have a calculator on their phone? Anything?
85%.
85%. What did we just say? What did we just say in part C? It's unlikely in 500 trials. So we only did one, right? This one student took an SRS. So what do you think about your teacher?
She's lying.
Yeah, she's absolutely a liar. So there's strong evidence based on part C.
Oh, I read that question totally wrong. Never mind.
It's okay. That the teacher is not telling the truth. Okay, so one more time. Can we get 85%? Yes, it is highly, highly unlikely. So if this student digs into this bag and gets 17 red chips on the first try, that is a very high suspicion that the teacher is lying. That's all it's saying. Could it happen? Yes. Yes. Okay. There are 20 chips in there. It could be 20 red, 20 out of 20, but that's likely not going to happen. Okay. All right. The next page is just filling in. There's not a lot to write. Let's do these 2 pages and be done. Okay. So strictly speaking, the sampling distribution is the ideal pattern that would emerge if we looked at all possible samples of size 20 for our population of chips. A distribution obtained from simulating a smaller number of random samples, like the 500 values of p hat. is only an approximation to the sampling distribution. One of the uses of probability theory in statistics is to obtain sampling distributions without simulation. We'll get to that theory a little bit later. The interpretation of a sampling distribution is the same, however, whether we obtain it by simulation or by the mathematics of probability. The following figure illustrates the process of choosing many random samples of 20 chips and finding the sample proportion of red chips, p hat, for each one. Follow the flow of the figure from the population at the left to choosing an SRS and finding the p hat for the sample, to collecting together all of the p hats from many samples. All right, so the first one shows the population distribution. We told you in the bag red was 50%, so 100 red, 100 blue. All right, then they did an SRS. The first SRS of 20 that they had was 8 out of 20. The second SRS they did was 11 out of 20. And then these little dots just means they did it over and over and over again until they got to this one. And that was your 500 that you had a while ago. Okay, so this is the beginning. We know that it's 50-50. This is each SRS. And remember, they did 500. This is all 500 together. That's all they're telling you to look at. All right. So the first sample, this first graph right here, has a p hat of 0.40 or a proportion of 40. The second sample is a different group of chips, so they put them back in and drew them again. And the second 20 that they drew out had a proportion of 0.55. They did this a million times. The dot plot shows the distribution of the values of p hat from 500 separate SRSs. So then they took all of these samples that they did and they plotted them on this dot plot. And that's what we're going to do with our chips. Okay. Again, of size 20. This dot plot displays the approximate sampling distribution of the statistic p hat. Okay. As the figure shows, there are 3 distinct distributions involved when we sample repeatedly and measure a variable of interest. The population distribution gives the values of the variable for all individuals in the population. In this case, the individuals are the 200 chips. And the variable we are recording is the color. Our parameter of interest is the proportion of red chips. This is it. This is the last bit. The proportion of red chips in the population. And remember that the population percentage was 0.5, and that's just p. That's not p hat. So population is represented by p. Each random sample that we take consists of 20 chips. The distribution of sample data shows the values of the variable color for the individuals in the sample. For each sample, we record the values of p hat. So that's the proportion of red in your sample from all possible samples of the same size and display them in the sampling distribution. Be careful, this is important, be careful. The population distribution and the distribution of sample data describe individuals. A sampling distribution describes how a statistic varies in many samples from the population. And we're going to stop there. We'll do our check your understanding tomorrow and finish this section up. Hopefully it won't take too long. Okay, it's still a lot left, but we'll try to get it all finished up. All right, I'm going to stop recording.